Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about general method for the structure determination of alkalides, and in that we have seen step by step we are discussing. Number one is a molecular formula. We know that how to determine, how to derive molecular formula that we have discussed in this particular as well as in the previous lecture also while studying the general method for the structure determination of the terpenoid as well as structure determination for citral. 2 times we have learned as well as 3rd time also we have learned. And the next point we have discussed about the detection of unsaturation, and as we know that detection of unsaturation is a very easy to identify whether the compound containing carbon-carbon double bond or multiple bond. There are two tests we are performing for the detection of carbon-carbon double bond in a alkaloid. Let us see over here. One is a bromination, another one is a hydrogenation. These two reactions gives us the information about how many carbon-carbon double bond present in the unknown alkalides. So hydrogenation or bromination, suppose your material, starting material or the substrate consume 2 moles of bromine, that brown in color get disappear. It means that the alkaloid containing 2 carbon-carbon double bond. If only one equivalent of bromine is consumed across the against the substituent, it means that there is only one carbon-carbon double bond is present in the alkaloid. That's it. So in this way we can easily identify, we can easily detect the presence of carbon-carbon double bond in the alkaloid. That's it. Now next point what we are going to discuss today or right now is look at here. That is a point number 3rd, nature of oxygen. As we know that if the molecular formula containing oxygen atom, then that oxygen atom present in a different functional group. As we know that the oxygen can be involved in hydroxyl group, it can be involved in carbonyl group. Suppose if it contains alcoholic, if it contains hydroxyl group, it may be alcoholic or phenolic. 2 kinds are there. So if this is there, alcoholic and the phenolic, how we can distinguish? There is a one chemical test used for distinguishing between phenolic and the hydroxyl group from each other. So that's the way. Another one is a carbonyl. Carbonyl also present in a 2 form. One is aldehydic, another one is a ketonic. But how do you distinguish between or how do you distinguish aldehyde from ketone? So there is also some of the reagent which can easily, from which we can easily identify, we can easily distinguish aldehyde from ketone. As we know that silver mirror test, it is one of the best classical method or the test for the detection of aldehyde from ketone. As we know that, then it may be present in carboxylic group, or it may be present in ester group, it may be present in amide group, it may be oxygen may contain lactone, it may contain a lactone, it may be methoxy, it may be dimethoxymethylene. So these are the various forms, various functional group oxygen atoms are involved, and therefore there is a need to distinguish, to identify the nature of oxygen atom in which form it is present, because there are the different functional groups along with that oxygen, and therefore it is very necessary to find out along the molecular formula containing as oxygen atom, it is there is a need of identification of that oxygen atom in which functional group it is belonging or it contains. So that's the thing. So suppose let us begin with first one, that hydroxyl. Suppose it is present in the hydroxyl group. Let's see here OH, that is a hydroxyl group, as we know that this is a hydroxyl group, right? And hydroxyl group, do you know hydroxyl group, suppose that oxygen atom along with that hydrogen atom may be as a hydroxyl group, and that hydroxyl group may be in a two type. It may be alcoholic, and it may be as a phenolic, right? Phenolic. This, which one is alcoholic and which one is a phenolic? How do you distinguish alcoholic from phenolic? There is a one test. General method, suppose if you treat that hydroxyl, if you perform as a derivative, if you prepare as a derivative, or if you treat the reagent like as a acetic anhydride or acetyl chloride, phenolic as well as alcoholic, that hydrogen atom get replaced very easily, and you will get as a formation of the derivative, that is a acetyl derivative, indicate that there is whether it is a monoacetyl, diacetyl, or how many number of hydroxyl groups are present in the alkaloid. We come to know that, but the question here, listen carefully, how do you distinguish this alcoholic, or whether it is a alcoholic or whether it is a phenolic? There is a one neutral. If you have you heard about that Fe, neutral FeCl3, if you add here FeCl3, suppose you have you don't know what is the nature of that, or whether it is a suppose aliphatic or aromatic. Suppose alcoholic, they are the aliphatic, and phenolic means the hydroxy group attached to aromatic ring, attached to aromatic moiety, and that's the thing over there. And therefore, how do you distinguish between this, whether it is aliphatic or aromatic hydroxyl group that are, suppose here, if you treat this compound with a neutral FeCl3, that is ferric chloride, what do you get? There, suppose there is a color is obtained, like as a color maybe as a blue or green, or maybe as a violet color. Violet color, it clearly indicates this is a phenolic group. Phenolic. So that is one of the classical method to distinguish alcoholic group from the phenolic, or we can distinguish from aromatic, aliphatic or aromatic phenolic groups are there. So in this way, very clearly, suppose you have again take down as a general formula of that ROH, may be alcoholic or the phenolic, we don't know. But if you treat this compound with dehydrating agents, like as a concentrated H2SO4 or P2O5, you are going to get, according to as a CH-9 rule, dehydration means what? Removal of the hydrogen atom from the substrate, and we are getting as a eliminated product, and that product predominantly according to as a CH-9 rule. And what the CH-9 rule tells us, that in an elimination reaction, more substituted alkene is obtained as a major product and less substituted alkene is obtained as a minor product. So that's the rule. Tell us that rule is nothing but as a CH-9 rule. This is for elimination reaction. And E1 reaction, E2 mechanism we already learned in our previous classes, so no need here. Just remember, if we are distinguishing whether it is alcoholic OH or phenolic OH, that's it. Only one reagent is a ApCl3. If you add, if it gives the color, blue color, green color or violet color, whatever it may be, that clearly indicate that the given compound is a phenolic, means aromatic hydroxyl groups are present, and by this method we can easily detect alcoholic and the phenolic nature of the alkaloids. Now let us see another one, second one. Suppose the second one is a carbonyl group, C double bond O, and C double bond O, as we know that, suppose here is a R and here R, that is the carbonyl group, suppose here. So again carbonyl group, again it is present in aldehyde as well as ketonic. Then again question arises, how do you distinguish this is aldehyde and this is a ketonic? There is a one test we already learned this under terpenoids section, I think 3.5 somewhere. So where we already distinguish that aldehyde from ketone. Suppose we don't know whether it is aldehyde or the ketone, perform the one test, do the one test. What is that test? Silver mirror test. Take the unknown compound in the sample tube or in the test tube, add the silver mirror solution, that is a ammonical solution. If there is a what we can call it as a silver AZ that is deposited at the edges of the test tube, that is called as a silver mirror test, that clearly indicate that given compound containing as aldehyde group. So that's it. So this is the way you can distinguish aldehyde group from the ketone. That is the one thing. Then carboxylic group, as we know that, third one, C is a carboxylic group, COOH. As we know that this is a carboxyl group, and carboxylic group in an organic compound, even though in a general organic compound, how do we perform the test in the laboratory? While performing as a qualitative analysis in the laboratory, there we are using one reagent, that is a 10% sodium bicarbonate, that is eating that powder, or what we can call it as a sodium bicarbonate. If it dissolve with the bubbles or the effluxes of CO2, that clearly indicate that there is a carboxylic group is present. And how many number of carboxylic groups are present, again you can treat with the against with the standard alkali, and you can find out the number of carboxylic group are present in the given unknown compounds. That's the way to determine that carboxylic group, and that also we have learned or see under the section C under the terpenoid section 3.5. Then now very what we can call it as a very important, we are going to start. The next one is a ester, amide, lactone and lactone. These are ester, amide, lactone and lactone. First of all, let us see what do you mean by the ester, amide, lactone and lactone. So I think ester you might be knowing. Let us see, first one is the ester. What is the general formula of ester? The organic compound having general formula RC double bond O dash is known as a ester. Everybody knows that it is an ester, right? Now second one is amide. Amide also most of you might be knowing. The amide having as a general formula RC double bond O NH2, that is the primary amide, secondary amide and tertiary amide also known, but we are not going to go into detail of that. But here amide means it having as a general formula RC double bond O NH2 is known as amide. Now is a lactone. What do you mean by the lactone? As we know that this is a ester. It is open chain compound, no doubt about it. For example, let us see here CH3, C double bond OO, then CH2CF, that is the ethyl acetate. As you know that this is open chain. But when it is the ester group is involved in the ring formation, that type of the structure is known as a lactone. Remember, please remember here, lactone means, suppose let us see here, we have a CH2, then O, oxygen atom, and then here this, not this one. So if you see our carbonyl group and this one, you can attach CH2N like this. So best way you can remember C double bond O. This is a 6-membered ring I am showing, and this is nothing but as a lactone. Remember, maybe as a 6-membered ring depending upon the strain. So there is a, suppose as a 5-membered ring, or maybe as a C double bond O. This is a 3-membered ring. So that type of the rings are known as a lactone. Remember, these all are the lactone. And what do you mean by the lactone? Remember the spelling here. Lactone, UM, indicate this is a amide. You know that. Everybody knows that. The amide. Amide is a open chain ring, right? Open chain or aliphatic you can call it. Not aliphatic. Open chain you can call it. Here open chain, this type of the structure is known as a ester general, and when it is present in the cyclic form, that is known as a lactone. That's it. And now amide, open form of that amide, that type of the organic compound is amide. When it acquire the ring form or a ring structure, then that ring structure is called as a lactone. Remember here the C double bond O instead of NH you can write over here. So this one is a CH2 and N. N means number of CH2 methylene groups are there. If 1 is there, 3 member, 2 is there, 4 member, 3 is there, 5 member, 4 is there, 6 member. So let us see here NH. So this type of the structure is called as a lactone. Remember, this is a structure of lactone. Understood this? The concept of lactone and lactone. Now I hope you understood it, right? Now lactone means cyclic form of this type of amide is known as a lactone, and the cyclic form of ester is known as a lactone. That's it. That's the trick you must remember while studying the organic chemistry. Okay. Now let's begin with that. The D part, that is the thing we are discussing over here. What is that things we are discussing here right now? The nature of oxygen we are discussing, and among that nature of that is a ester, amide, lactone and lactone. This is the point we are discussing right now, and these groups can be detected and estimated by observing the product of their alkali hydrolysis. That's so simple. These group can be determined and estimated by observing the product of their alkali hydrolysis. That's it. Let us see over here. First one, we know that the general formula of ester is this one, RC double bond O R. That will be treated with, or what we can call it as this is a structure of ester when it is heated with strong alkali like as a sodium hydroxide OH. So OH is going to attach over here like this mechanism here, and now this is revolving around it and remove as a alcohol, because ester is made up of by acid and the alcohol, and therefore the resulting compound will be obtained RC double bond O, sodium salt of that acids, and the alcohol ROH. Alcohol we are going to get in this case. So because that sodiums they are the, and if you acidify it you will get the acid back. So this is the general way of determining acid. So number of acid present in the compound, again then go for acid treatment, then find out the number. Now let us look at the second one is amide. As we know that RC double bond O NH2. This is a general formula of amide once again. And now again boiled it or reflux it in presence of sodium hydroxide alkali. What alkali will do over here? OH minus is going to attack on that carbonyl group. The electrons are revolving around that oxygen atom and there is a evolution of that ammonia. So you are going to get once again RC double bond O, Na plus over there minus charge, and then there is a NH3 hit. Still there is a no smell of ammonia. As we know that the smell of ammonia is very irritating to our nose, and therefore the completion of reaction confirm if the evolution of ammonia is stopped in the during the hydrolysis. All these are the hydrolysis reaction. Now let us move on third one. That is third one is a lactone. That is a lactone structure over here. Let us see over here R, then CH, CH2, C double bond O. I am writing over here. Not here again is once again CH2. Here is written as a CH2, and then here O, then C double bond O. This is a structure is written over here, and this if is heated with water H2O, what is going to happen? This bond is going to break because the bond, the weakest bond present in this ring formation is a oxygen and the carbonyl carbon, and therefore what do you get over here? Here you are going to get R, CH, OH, then CH2, C H2, C double bond O, OH. Is alpha, beta and gamma hydroxy, alpha, beta and gamma hydroxy. This is gamma lactone. Generally this is a gamma lactone, and after the hydrolysis we are getting as a gamma hydroxy carboxylic group. So similarly on the basis of this we can write the structure of lactone. Let us see the structure. Fourth one is a lactone R, CH, then CH2, CH, sorry here is only as a CH because carbon never shows the 5 bonds. So here you can write the NH, then C double bond O, that's the ring. And now again this ring is going to break over their heat in presence of the water. What do you get? Same R, CH, then NH2, then CH2, CH2, then C double bond O and OH. From water, hydrogen atom go along with that NH, so it becomes as a NH2, and hydroxy group OH is attached to this carbonyl group and that becomes as a acid. So in this way, from hydrolysis, by studying the hydrolysis product, we can easily detect, or we can easily find out the whether it is acid, amide, lactone or the lactam in the given. Now let us move toward the next point. And now so far we have seen up to the D point. So now the oxygen may present in the methoxy form or methoxy group. Let's see how we can identify, we can detect or we can find out the methoxy group if it is present in the group. That is the E point, that is a OCH3, that is a methoxy group, right? This is a methoxy group. Methoxy group. This is a methoxy group. And now the presence of methoxy group and their number may be determined by Gisels method. By Gisels method. By Gisels method. By Gisels method. This is the one of the method he discovered first time, he invented first time, and therefore name is given to that reaction, that is the Gisels method. The presence of methoxy group and their number may be determined by Gisels method. A known weight of alkaloid is heated with concentrated HI when following reaction takes place. That as we know that suppose you know that RO and CS3 methoxy group is there, and this will be treated with concentrated HI, hydrochloric iodide. HI means hydrogen iodide. Just heat it, concentrated HI. So the reaction takes place. You are going to get R, then ROH and plus ROH plus methyl iodide, CS3I. This is a form of precipitate. This is a form of PPT we got over here. And the resulting methyl iodide. This is a methyl iodide, right? This is a methyl iodide. This is a methyl iodide. The resulting methyl iodide is passed into an alcoholic solution of AgNO3, that is a silver nitrate, which when AgI gets precipitate, let us see over there. Take down the starting compound is a methyl iodide. We add the reagent AgNO3 alcoholic, this one, and now when heated it, what do you get? Methyl nitrate CS3NO3 and plus AgI. This is in the form of precipitate. This is the form of PPT we are getting over there, PPT. And the precipitate of AgI is dried and weighed. From the weight of AgI, number of methoxy group are found out. Very simply we can find out by using this formula. The precipitate of AgI is dried and weighed. From the weight of AgI, number of methoxy group are found out. Therefore 1 mole of, let us see here, 1 mole of AgI, which we got here, precipitate, and then there will be a 1 methoxy group. 1 methoxy group. 1 methoxy group means OCH3, as we know. And we know that the 1 mole of AgI, the molecular weight of that AgI is 235 gram, and methoxy we know that only as 31 gram. And by using the mathematical formula, we can find out the one amount of methoxy group. Mathematically we can find out it. Weight of AgI divided by weight of substance substance, as we know that weight of the AgI, we know that it is 235 gram, whereas weight of the substance we have taken is a 31 gram, right? So by calculating this, we can find out this, we are going to get dash dash in the number of gram, and by using that the amount of methoxy group. Now in the second formula we can find out amount of methoxy group, amount of methoxy group, amount of methoxy group, methoxy group is equal to, or the number of methoxy group we can call it here, number of amount, not number of methoxy group. Number of methoxy group can be found out by using this formula. So here we can take down here amount of methoxy group into molecular weight, amount of methoxy group OCH3 group into molecular weight divided by 31. By using this formula we can easily find out the number of methoxy group in the given. There is one problem is given, so that problem you can find out very easily. How many methoxy groups per molecule are present in an alkaloid when 4.24 milligram of alkaloid is treated with hot concentrated HI to yield methyl iodide, which is passed into an alcoholic solution of AgNO3 when 11.62 milligram of AgI is obtained. Molecular weight is given 340, and therefore amount of OCH3 group is equal to weight of AgI divided by weight of substance into 31 divided by 335 is equal to 0.00162 divided by 0.00224 into 31 divided by 335, and therefore we are getting 0.3615, and therefore number of methoxy group is equal to amount of OCH3 group into molecular weight divided by 31, and therefore 0.3615 into 340 31, and you will get as a 4. So in this way we can find out. So that is there. And now the last one is the nature of methylene dioxide. So that is the final point we are discussing over here among the nature of oxygen atom. Let us see what is that, or how we can determine, or how we can find out the presence of methylene dioxide group in the given compound. Let us see, this one is a F, that is a CH2, then O. This group is known as the methylene dioxide. This group is known as a methylene dioxide. Methylene dioxide. This is a group we know that in the given. The presence of this group is indicated by the formation of formaldehyde when alkaloid is heated with concentrated H2SO4 or hydrochloric acid. By the formation of formaldehyde when alkaloid is heated with H2SO4 or HCl, what you are going to get here, generally this one CH2OO, not this, and this will be treated with the concentrated 2HO, 2 molecules of water and H2SO4. You are going to get one of the intermediate is like this, H2CO minus, and then O minus over here, and that is unstable compound, and that is there is a elimination of water, and you are going to get the formation of C double bond OH, that is a formaldehyde. formaldehyde. This is the compound we are getting over here, formaldehyde, and therefore, so the qualitative estimation of formaldehyde gives the number of methylene dioxy groups present in the alkaloids. So these are the some of the method for the detection of that group. I think we have studied the nature of oxygen atom, with how the oxygen atom involved in a different functional group, how we can perform different tests and to detect the nature of the oxygen atom involved in that. So I think with this, let us stop today here. In the next time we will see the nature of nitrogen atom, because these alkaloids are the basic in nature, and therefore that is a very important point we are going to discuss in the next lecture. So till then, have a nice day. Thank you.